So I'm going to talk about exceptional field theories and the double copy. This is based on this paper with Kim and Lee, just out quite recently. So I've got to tell you first, some motivation and context. We're used to combining electromagnetism and gravity using Kaluza-Klein theory. And what you get when you do that is another geometric theory. You get gravity back. But you could have asked the question, given the fact we've got all these supergravities, where we don't just have electromagnetism, but we have higher form potentials and higher form field strengths. What's the equivalent of Kaluza-Klein theory? What is a geometric package for combining metrics and higher p-form potentials? Okay, so double field theory does this job when we've just got a two-form gauge theory, the NS sector of string theory, and it's a sort of Kaluza-Klein lift of supergravity itself. Now, it turns out that it doesn't lift to a simple ordinary Riemannian theory, but it has some additional structure, which I'll discuss in a minute. And then more than that, when we've got all the p-forms that exist in supergravities, and in particular in 11-dimensional supergravity where we have the three-form, you can ask, what does that lift to? And that's what exceptional field theory does. So why is that relevant for this conference? Well, recently there's been this whole set of interesting set of works called the classical double copy, which is this interesting map between classical solutions in gravity and solutions in Yang-Mills or indeed some abelian subsector. So, and the bridge that allowed this to happen was this thing called the Kerr-Schild ansatz. It was a way in which you can linearize gravity and capture the non-linearities of the classical solution of gravity and show that these are actually mapped to solutions in a field theory. So then, okay, that works for ordinary gravity. And the question which I want to then try and answer is, how do we construct a double copy for the combination of metric and p-form potentials? My claim is that the package of exceptional field theory will do it for you. Okay, so I'm going to introduce double field theory rather lightningly fast. There's lots of reviews available, but these slides are just going to give you a sort of an overview. So double field theory combines the metric, the B field and the dilaton on equal geometric footing. It does so by doubling the dimension of the space, but then you need this ODD structure to be present on the space. Excuse me. Okay. And then later you do a sort of Kaluza-Klein reduction and reduce it back to D dimensions, and then you get the usual set of fields. Okay. But along the way, we've generalized the metric and we've generalized the local transformations into what's called generalized diffeomorphisms. So this is the generalized metric. It's the package which tells us how to combine metric and B field together into one geometric object. And then we have a sort of generalized things that you're used to, an action, Ricci scalar, and so on, all in terms of this generalized metric. And that will reproduce for you the things that you like in gravity. When we extend this to M theory, then we've now got to unify a metric and C field with higher forms. And it turns out that we can't just double the space. And it needs to be done on a dimensionally dependent basis. I won't go too much into the details of the dimensional dependence, but what I'm going to do here is consider a four-dimensional space. And it turns out we actually need to extend the space by 6 dimensions. Okay, and here that gives a total of 10. So my usual 4-dimensional space ends up being replaced by a 10-dimensional space, which is a combination of vectors and 2 forms. These are the coordinates on the space. This forms a 10 representation of SL5, which is actually the usuality group associated to 4 dimensions. And this is the package that you need to see. So through the background of EFT, and I've not gone into it in too much detail here, it says on that 10-dimensional space, the appropriate metric is this object M. These indices here run 1 to 10. And this upper block here is 4 by 4. This is 6 by 6. And obviously then these are 4 by 6. And it tells you how to combine C and G together into components of a higher dimensional metric. Okay. So, and then you can then use that metric, and then people did a lot of work and wrote down actions for this thing. This is the action. More details about the action. I'm just showing you these things exist. And then the equations of motion are given by a variation of this action. Now there's one small caveat, which is that that metric did not have as many independent components as you'd normally expect. It was a constrained metric in order to fit in with this SL5 structure. What that means is that when you vary the action, you must vary the metric while still maintaining that SL5 structure, which means that we need to introduce a projector on the variation of the metric. K was just the variation of the action. And this will project you down so that you don't end up with an overly constrained system. So the actual equations of motion are just given by this R hat being 0. And this is the projector, which is again in terms of the metric. And this Y tensor is an object that's proportional to the structure of the theory, okay, related to the structure of the theory. So why do we do all of this? In repackaging it this way, so all I've done is repackage, I'm going to go back to the crucial point, the metric and C field in this new geometric way. What we can do is then come up with a more universal Kerr-Schild ansatz that will combine the metric and C field together in one thing. Okay. So for those of you not familiar with the Kerr-Schild ansatz, this is almost it. The usual Kerr-Schild ansatz does not have this projector P. And this was done way back in the 1960s, and it's been used to find a whole host of very interesting and non-trivial solutions. Its remarkable property is that basically when you make this ansatz into your gravity solution, then you actually sort of end up linearizing the system, and some combination, I'll write it down in a minute, of phi and k will actually end up obeying Maxwell's theory. Okay. So what we want to do is come up with an ansatz for our generalized geometry that will have all the properties of the Kerr-Schild ansatz, but still respect all of the structure that this exceptional field theory has in combining the metric and C field. Okay. So this is the ansatz. P is this projector that was necessary from before. And when you actually work through it and see what's required to make the ansatz work, you see that K is generalized null. Okay, so for those of you familiar with the ordinary Kerr-Schild ansatz, you require that K is a null vector. Here it's only generalized null because it's null including all the extra dimensions that you've added on to make this theory work. Okay, so from a Kaluza-Klein perspective, it's null in 5 dimensions, not just null in 4. And then we need an additional constraint, which is that this combination, which we call Q, has to be nilpotent. This is a technical thing just to make things work. Okay. When we do that, we can just go through a whole host of theories and see that will change the projector and see what this ansatz is. So the first case to check is what everyone's known about since the 1960s, that if the projector is trivial, it's just the identity matrix, then this reduces to the Kerr-Schild ansatz for GR. And then this is just an ordinary null thing. The people who are familiar with the classical single-double copy relation will then tell you that the phi k is what you identify with the Maxwell field A mu. And then you come up with all sorts of solutions in electromagnetism, and then later addressing it in non-abelian, with some non-abelian structure, come up with solutions in Yang-Mills corresponding to this. So the combination of phi and k is what you end up mapping to in the single copy. Okay. So the next thing to try is this double field theory. Here again is the metric, which combines the usual metric in the B field. This is some additional structure required on the space. And then the Y tensor required for that projector is given here. And in double field theory, something happens which doesn't happen in all theories, is that projector factorizes. So you get a pair of projectors. And in fact, this corresponds to a left and right decomposition of the string modes. Okay, so recall that these fields are actually the zero modes of the closed string. We're used to the fact that the closed string decomposes into its spectrum to left and right movers. This factorization of the projectors associated to that. And in fact, I'm going to go through, so we sort of keep on going here. When we get to the end, I'll just go to this formula here. These two one forms that you have are eventually what will go on to produce two one forms in the single copy. You'd eventually show that these are related to the two vector fields in the theory. And this corresponds to exactly what you know about string theory, that you can think of two open strings giving you a closed string. And ultimately, in terms of amplitude physics, this is related to the KLT relation. Now, so it's no surprise that this works for G and B field, that we could then come up with a single copy involving two vector fields and get both G and B. What's completely not obvious is that if you do the same thing for M theory, where we have a metric and a C field, we have no strings with left and right movers, we have no open closed duality, that you'd have a chance of ever doing it for the fields in M theory. Okay, but what we learned from doing exceptional field theory is that if it works for DFT, if it works for double field theory, the same structures persist in exceptional field theory for M theory. Okay, so we can take the ansatz that we had before. I'm just going to go back to it. Yeah, here we are, this ansatz, where M is our generalized metric combining G and C in the form that I've shown you, and P is a particular projector, and K will be a null vector in the 10 of SL5, and we can work with that. And here I've chosen a flat background. This is my M0. This is the background from which I'm then looking at the fluctuations of. And the null vector are parameterized like this. So the null vector in this theory will have a part in the 4 and a part corresponding to two forms in the additional 6-dimensional space. Okay, so mu runs from 1 to 4. This is anti-symmetrized, so that's got 6 components, giving us 10 overall. Okay, this is just some identities involving epsilons, and then you get the fact that K must be null like this, and then that relates to the 4 vector, which is the space that you're used to, and this additional set of 2 forms that you've now got in your space. Okay. You go through the structure of EFT, and then that will tell you what this projector is. In this instance, it's given by some epsilon symbols. And you work through this, and what you find is the following thing. So I know this has been a very quick lightning review of EFT. I can't really do it justice in 10 minutes, but I wanted to give you the flavor of its purpose and actually present some results. So if you've switched off on EFT, you can now switch back on again. Here is a map between G mu nu, the metric, and the 3 form, and L mu, a 1 form, and K mu nu, a 2 form. Okay, and some scalar field. And these objects, L mu, K mu nu, and phi, are the things that will be associated to the single copy eventually. Okay. So here I have a map that's very nonlinear between some null vectors, two forms, and a scalar field. Now, just to make sure that we're being sensible, if I set K mu nu equals 0, then the C field goes away, because the C field is the anti-symmetrized product of L and K. This term goes away, and then this term, because L is null, also goes away. And we are left with the traditional Kerr-Schild ansatz. Okay, so that's the first good thing. It does what it says. If C is 0, we just get ordinary Kerr-Schild, and phi L will be the thing that will be associated to the single copy and eventually dress it to make it into a Yang-Mills field. Okay, but we can now do better, because what this says is that actually by including K, we can now include the C field. Bear in mind, in supergravity, if I switch on non-trivial C field, I'll get back reaction on the metric and so on. So that's why it's nonlinear. What's nice is that this map is so simple. When we then insert this into the full nonlinear equations of exceptional field theory and ultimately supergravity, then the equations of motion reduce to this linear set. So this is a huge amount of work to show that, but that's the result, from which you can then identify A being given by phi L mu to be a Maxwell field, and B mu nu to be given by phi K mu nu. Later I'll discuss why this phi is the same and what you could do and what happens if you make that different. Okay, but what we've got then is a single copy for metric in C field. We've got a Maxwell field, and we've got a two-form field, and then solutions like this will give us solutions of M theory. And just to show you, this is perhaps the most canonical example of an M theory solution. It's the membrane. This is the solution. That's the 11-dimensional metric. That's the C field. And now I'm going to look at a sort of a reduction of that, because I was just working in 4 dimensions. So I reduced that down to 4 dimensions. And I just then find that the single copy solution that I had is just A0 equals phi, B12 equals phi, and then identify phi with H. And then I reproduce, just with this simple harmonic function, if phi is a harmonic function, this full nonlinear set, this nonlinear solution of the M2 brane. Okay, and that is what it's good. So then when we look at what that solution looks like, it's like having a plane of electric charge, which is what the Maxwell field does with its harmonic solution, but smeared over 2 dimensions. And then the other solution is that of a magnetic string smeared over 1 dimension, and the 2 planes of sourcing the A field and the B field sitting on top of each other. This is a particular choice of solution. If you had different charges between the Maxwell field and the 2 form, so here they're the same, this is related to the BPS condition. It's because the tension of the membrane, the gravitational part, is related to the charge of the C field. So in other words, in terms of the original gravitational solution, this harmonic function H is the same harmonic function as appears in the gravity solution. So going into a slightly more general thing, if the 2 form has got a different harmonic function to the 1 form, then that'd be a non-BPS solution, we suspect. Okay, and that's brought me up to my 20 minutes, and I don't like overrunning. So there's a whole set of things to look at, different solutions. One can look at more complicated exceptional field theories that would involve 6 forms and a whole spectrum of things. And what we can also do, which I think is a very interesting avenue, is to look at dressing these fields and look at a non-abelian interacting theory between the one forms and two forms and relate that to amplitude physics in the full 11 dimensions involving G and C. That's not quite so easy to do, but what's interesting is that we don't have a string theory background. We don't have left and right movers, the idea of open and closed string relations, and yet we can form this classical Kerr-Schild double single copy relationship. Thank you.
Let's thank David. So we have time for a few questions. Max.
Yes, I have a couple of questions. So the first question is, you talk about the metric Kerr-Schild, right? I was wondering if you can apply this for the flat metric, for example. And the second question is if you can apply this for the fermionic sector of supergravity.
So you can certainly do it for the flat metric. The only issue would be is that if your metric is flat, the solution won't allow you to have non-trivial C field that's not pure gauge, because the equations of motion are such that I can't have non-trivial H flux without back reacting on the metric. But you could certainly, look at things like that. That's no problem. This is quite a general solution, and you can play with this map of what you do with K and L and this harmonic function phi. So you can, you go to the paper and have a play with this map and see all your favorite solutions or not.
Okay. Okay.
In terms of fermionic sector, that's a very good question. And there is a fermionic version of EFT. I don't know how fermions work in the single double copy. So good question. I don't know the answer.
Okay. Thanks a lot.
Shall we have Donal? I think that was the next hand up.
Sorry, to mute myself. Hi, David. Just a super quick thing. Is there any, would there be any obstruction to going to spacetimes with, well, funny signatures like two time directions and many space directions?
Right. So, okay. So I didn't discuss signatures. I'm in good old 1,3 here. Exceptional field theories have been written down in arbitrary signatures. The Kerr-Schild ansatz, however, requires this null vector to linearize. So you need something. You need to be able to make something null. So you've got a problem if it's completely Euclidean.
Yeah.
If you've got two times, I might be happy with that. I can still go null.
Yeah.
And some people like two times. Now, so there's lots of possibilities there. And I come from the EFT community. We work hard at sort of going through all the different cases, and some cases there are all sorts of weird signs and some imaginary things crop up, but it's all there in the literature now.
Okay, great. Thanks.
I think Callum was next.
Yeah, hi. Very nice talk. I think you may have already responded to this with your answer to Max's question, but I'm going to ask about supersymmetry. So the way supersymmetry usually works in the double copy is that you inherit it from the single copies. But in 11 dimensions, it doesn't seem like you have any super multiplets that the single copy could live in. Have you thought about this and how this would work?
Yeah, right. Okay. So this sort of fits into the question of how do I dress A mu and B mu into not just having, well, how do I dress them in the sense of make them supersymmetric, make them non-abelian? Well, you can easily, I mean, this is in 4 dimensions. You can easily make a vector multiplet, and you can make tensor multiplets. That's not such a big deal. Now, the interesting thing is how you make them interacting. So there has been work done by Henning Samtleben and collaborators where they formed an interacting supersymmetric theory with A and B. This was done actually in the context of the tensor hierarchy in supergravity. So people have formed supersymmetric multiplets with interacting A and B fields that are non-abelian. Now, in the end, they wanted to do that actually for the M-theory 5 brane, and that turned out not to quite work. But it may work here. So, yeah. There are possibilities. What should I say? We've not investigated whether they're right yet, but there are things to try.
So does this construction only work in sort of when you compactify down to 4 dimensions, or does it also work, could you make it work in 11 flat dimensions?
Right. So the particular, right, the general construction, the Kerr-Schild ansatz, that's universal, should work in all, well, nearly all dimensions. And the details of the generalized metric, however, I skipped a slide because it works like this. So the metric, the generalized metric parameterizes the coset G over H. So I had this one here in 4. The generalized metric parameterizes cosets of these things. So yeah, so you can do a lot. As you go up, these dimensions grow, and you had to have more and more extra dimensions, and that allows you to include higher and higher p-form fields. So this is the current state of the art in EFT. To go up one more, we need E9, which is infinite dimensional. And, you know, that's a challenge, but people are probably going to do it. So the short answer is yes. Given current EFT technology, we could do nearly any dimension you would want to. Technically, the complexity gets larger and larger. For example, just E7 is 56 dimensional. And if I show you this metric is relatively easy to cope with. As you go to those higher dimensional cases, you end up with more and more non-linearities in C, because C interacts with C6 and there's other interactions. And all of that gets packaged in this metric. But the structure should be universal. That's the great thing about EFT. If it works for one exceptional group, it will work for them all.
I see, thanks.
Okay, let's thank David again.
Thank you.